Hi, my name is Harper Brady, and my guiding question for this research project is, if the speed of light is constant, why do we observe the speed of light slowing down near the event horizon of a black hole? Basically, in simpler terms, I'm asking, is the speed of light actually constant? To answer this question, first we have to understand what light is. Light is a form of electromagnetic radiation that shows properties of both waves and particles. It is a form of energy, and visible light can be detected by the human eye. On a smaller quantum level, explained by quantum theory, which is the theoretical basis of modern physics that explains the nature and behavior of matter and energy on an atomic and subatomic level, we can see that light is made of photons. Photons are a type of elementary particle that serves as the quantum of electromagnetic radiation. These particles are massless, which explains why the speed of light is so fast and stays constant. Light used to be thought of as an electromagnetic phenomenon, but did not obey the same laws of mechanics as matter. Scientists struggled with this contradiction until Einstein came along. He observed that the laws of physics and the speed of light must be the same for all uniformly moving observers, regardless of their state of relative motion. For this to be true, space and time can no longer be separate, and this led to what Einstein coined as the term space-time. Space-time is a mathematical model that fuses the three dimensions of space and the singular dimension of time all into a single four-dimensional manifold. Space-time is basically just a physical representation of the four dimensions we live and perceive the world in. After coining this term, Einstein then moved on to develop his theory of general relativity, which stemmed from the theory of special relativity. Special relativity is a part of a larger theory of relativity regarding the relationship between space and time. It is based on two postulates. One, that the laws of physics are identical in all inertial frames of reference. This means frames of reference with no acceleration. The second postulate states that the speed of light, as observed in a vacuum, is the same for all observers regardless of the motion of the light source or the observer. Einstein's theory of general relativity that stems from special relativity describes gravitational force as a continual non-spatial whole of space and time. Basically, special relativity focuses on the velocity differences between inertial frames, and general relativity focuses on the acceleration differences between non-inertial frames. Special relativity applies to all physical phenomena in the absence of gravity, while general relativity explains the law of gravitation and its relation to other forces of nature. Now that we understand what light is, what space-time is, and the difference between general and special relativity, let's move on to how a black hole interacts and affects light. A black hole is a region of space where enough mass is contained within a given volume that the escape velocity exceeds the speed of light. Black holes contain an event horizon, which is the border between inside and outside of the black hole. Basically, the event horizon is the point of no return. Black holes are an enormous well of gravity, meaning that they affect almost everything around them. Black holes bend space-time and even seem to consume all phenomena, including light. Also, due to the extremely strong gravitational field of a black hole, time slows down upon approach and comes to a standstill as it reaches the event horizon. We view this phenomena as time dilation, which is basically the slowing down of a clock as determined by an observer who is in relative motion with respect to the clock. Basically, two observers view events happening simultaneously at different times. Neither is necessarily right or wrong. Naturally, you would assume that since time slows down for any object falling into a black hole, that light, which is made of photons, also just slows down. But this is not the case because photons are massless. They are not affected by gravity the way we assume. The theory of general relativity states that any massive object warps the space-time around it. Gravity doesn't directly bend light by influencing the motion of protons. It's just that the space-time around the black hole is warped and the light takes the shortest path. This makes the light appear to bend when it passes through the warped space-time around the black hole, but it's actually not bending. So if protons don't slow down and aren't affected by gravity, and they remain at c, the constant of light, what does this mean? In special relativity, the speed of light is a global constant that all observers everywhere will measure at the same value of c. In general relativity, this is still true, but only if spacetime is flat. If spacetime is curved, like what we see with black holes, then all observers everywhere will measure the same value of c only if the measurements are done locally. Basically, this means if I measured the speed of light at my location, I will always get c. This value will be constant, and this is true whether I am sitting still, riding a bike, or even falling into my own local black hole. But if I measure the speed of light at some point that is distant from me, like say from Earth to the nearest black hole, I will generally get a value that is different from c. Basically, light remains constant unless you're looking through the lens of general relativity. The speed of light just appears to slow down to the outside viewer. When measured locally, the speed of light will always remain c, meaning that the speed of light is always constant. It just appears to change depending on where and how you are observing. Thank you.